Hello ATS 315 students, Dr. Shragi here, and I am just going to show you how the practical 3 should have worked for you. So this was the assignment where you were computing geostrophic vorticity based on the height field. And to start off, we're going to just look in this program here for some of the action items. Your first action item was that you needed to read in your height data. So notice I already have the loop set up for you. You're reading in for rows from I equals 0 to I is less than num rows. Then for each of those rows, you're going to be reading in columns j equals 0 to j is less than number of columns. And then you just need to insert one line here that is going to read the appropriate value of height from that file. Well, then what we're going to use is an fscanf statement. We're going to be reading in from the file that we called fheight. And we're reading in a floating point number, and it's going to go into the variable height row I, column j. That's all you needed for that line. See how you're just reading in a floating point number going into height row I, column j. This will happen num calls times num rows times before you are done with all of the data. Then the next time you're going to go through and you're going to read in, according to this action item, all of the values from the array, from the file that was called latitudes. You're going to read in all of the latitudes. This is again just one line that you're inserting here. It's an fscanf statement. You're reading in from the file called flat. You're reading in a floating point number, and it's going to go into lat I. So there are num rows values in this array, and they each represent the latitude in degrees of row I. All right, here's that line that I wanted you to take out. There we go. So then you close the height file and the latitude file. Okay, now here is your first actual calculation. You're going to compute the value of the Coriolis parameter f for each of your rows from I equals 0 to I is less than num rows. So f is equal to, now according to the handout that you got at the beginning of the test, it's 0.00011456 times the sine of latitude. Now if we just did something like this, it would almost work. So here's that constant times the sine of latitude, but this latitude is in degrees, not radians, and according to the handout, the way you change degrees to radians is you multiply by 3.14159 divided by 180. So this section of the code right here is going to be changing your latitude of latitude I. It's going to become a latitude in radians. Sine of that times this constant will give you your Coriolis parameter at row I. All right, so that statement is now done. All right, this part of the program you didn't need to change. And now it's time to compute the geostrophic vorticity. Now you need to compute the geostrophic vorticity at all the grid points except right around that edge of your grid. In other words, you can't compute in the first row or the last row, the first column or the last column. All right, so first off, you got to replace this big long dash here with something that is correct. Now normally we would say for I equals 0 to I is less than num rows, I plus plus, which is almost right, but that would mean that we're doing the 0th row, our first row, and we'd be doing the num rows minus 1th row, our last row. But we can't do the first row and we can't do the last row. We have to do for I equals 1 to I is less than num rows minus 1. That way our first row is the 1th row, which is the second row of the data. And our last row that we'll be doing is the num rows minus 2, because we're doing it until I is less than num rows minus 1. In the same sort of way, for the columns, we normally would be doing for j equals 0, j is less than num calls, j plus plus. But in this case, it's going to be because we can't do that first column, column 0, now we're going to go from j equals 1. And we can't go all the way to num calls minus 1. We have to stop at num calls minus 1. All right. Time to actually compute the Laplacian of heights. The Laplacian of heights, remember, according to the handout, was the height to the north, plus the height to the south, plus the height to the east, plus the height to the west, minus 4 times the height in the middle, all divided by delta x squared. All right. Let's do that in words. Height to the north plus height to the south plus height to the east plus height to the west minus 4 times the height at row I column j, all divided by delta x squared. Well, up at the top of the program, if you didn't notice, let's go look at that real quick. Up at the top of the program, I already defined a constant called delta x. So we can go ahead and just use that. Where are we at here? Here we are. Here's where we were editing before. And I will go ahead and just make this delta x squared by doing it this way. I'm going to say delta x times delta x. You could do it a number of different ways, but that would be fine. Obviously, though this doesn't work, this is just me writing out some sentences here. Height to the north. Height to the north is the height at row I minus 1, column j. It's the same column, but it's one row before the row I, column j. Height to the south is the height at row I plus 1, column j. Compared to grid point ij, height ij plus 1j is the point to the south, plus height to the east. The height to the east is height row I column j plus 1. So from ij plus 1 is the point to the east, minus the height to the west. I'm sorry, plus the height to the west, which is height ij minus 1, minus the height at ij, well, that's the easy one. That's height row I column j, delta x delta y. All right, I got that step done. Fantastic. Now it's time to actually compute our geostrophic vorticity with our last, I believe this is our last action item, and that is g divided by, according to your handout, it's g over f, where f is of row I. Right? There's a different value of f at each of the latitudes, or each of the rows of the data, times this Laplacian that we just computed. So g was a constant I defined up near the top of the program. This is something we just computed. And then the Laplacian was something we computed in the line above. All right, I think that's the end of the program. So if I haven't made any horrible mistakes, we should be able to close. And we should be able to compile the program, which I called P3 rather than practical3. We didn't get any errors. And if we run it, we should get that value. And I believe that that is the correct value. Yes, it is. I'm looking at the handout. So our program works. So there really wasn't very much to change. It only took a couple minutes, but you had to understand what each of the steps meant. If you have any questions about this, just let me know.